Hello, now started to introduce my work. First is quantile average and weighted average. Previously, I introduced Daniel's work on the trimming and also Windsor's work on the Windsorized mean. And these are all linear combinations of order statistics. And indeed, since they are all symmetric, we can make a further classification. And here I call it symmetric weighted averages, but maybe symmetric L-estimator or symmetric linear combinations of order statistics is also possible candidate's name. I prefer this symmetric weighted averages because in the original test of Daniel, he used weighted average. So this is a way to acknowledge his contribution in this field. In this, because, for example, and for all values, we can find the corresponding symmetric pairs around the medium to form a symmetric quantile averages. And since the linear combinations of order statistics is just assigning weights in front of all the values, and so for a symmetric weighted average, we also we also assigning a weight in front of each symmetric quantile average. And for example, for an epsilon symmetric trim mean, if the order is smaller than the sample size times the breakdown point, and then the weight is we just assigning a zero weight. But if it is greater than or equal to the sample size times the breakdown point, and then we assign weight 1. So, and then if we want to extend it, the symmetric quantile average to asymmetric case, and then we can. There are two possible definitions. We call it quantile average, but there are two possible candidates. As I said here, the first definition is because we just adding another parameter, gamma, in front of the epsilon, and there are two possible choices. One is using the first quantile, and then or using the second quantile, 1 minus gamma epsilon. And if we use the gamma as 0.2 or 0.5, the epsilon as 0.2, and then the first quantile, the result is 0.5 times 0.2, and is 0.1. And the second quantile is 1 minus 0.2, and is equal to 0.8. So for the first definition, it is a little bit like that here. Here, a little bit like this is 0.1, and here is 0.8, since the 20% on the right side, and so it should be more. And for the second definition, we just also the first quantile is 0.2 and the second quantile is 0.9. We use a different color. Okay, here, and then 0.9. So obviously, the second definition trims much less compared to the first definition for large values. And so the first definition is preferred in this article because many common asymmetric distributions are right-scoot, probably besides the beta distribution. And so, and the first definition allows trimming only from the right side by setting gamma equal to 0. So then the quantile will be quantile 0. For a partial bounded distribution, it is just the bound. In most cases, it is 0. And then we just consider the second quantile, half of the second quantile, right? And analogously, we can extend the symmetric weighted averages into weighted averages similarly by assigning a weight in front of the quantile average. But this definition is asymmetric because it's asymptotic because for non-asymptotic case, maybe this can be non-integer, and it will be very complex relating to empirical quantile function. And furthermore, because the trim proportion for the right-hand side and the left-hand side are different, so we can separate the breakdown point into upper and lower parts. It is necessary in this case. And previously, the breakdown point just consider the infinity cases, and then we're replacing the infinity with negative infinity. We got the lower breakdown point. Before we introduce the most important part, I would like to first clarify 3 concepts in classifying distributions. And the first is the non-parametric distribution. Non-parametric assumption is not without any assumption. It still have some assumption, for example, finite second moment, finite mean, or bounded kurtosis, or continuity, or regularity, some regularity conditions or discrete distribution, and this regularity condition has the property that it does not have any specified parameter. It is just but it is just finite and infinite. It is like that. And for a parametric distribution, it means that the distribution is fully specified by Euclidean parameter, and in most cases we can find a corresponding probability density function or probability mass function or cumulative distribution function. And if we classify the distribution based on their characteristics, we can have another class of distribution called semiparametric distributions. And for example, the symmetric distribution, it is probably the first semiparametric distribution we studied, and the definition, if we using the quantile function, is just the first epsilon, and then the epsilon is equal to 2 times the medium, and then minus the quantile 1 minus epsilon. And this is the definition of the symmetric distribution in terms of quantile function. It have a specified relation, but it is not fully specified because I mean there are many parametric distributions fall into this class. And for a school distribution, it is also a semiparametric distribution. For unimodal distribution, it is very different because it is the definition is based on the signs of derivatives. Just consider, for example, here is a unimodal distribution. Before when the value is smaller than the mode, then the derivative, then the probability density function is greater. The derivative is greater than 0, and when the value is greater than the mode, then the derivative is smaller than 0 because it is monotonic decreasing. This indeed, we use this method. We can defining a new class of distribution based on the signs of derivatives. And first is the gamma ordinals, and we can define it as the partial derivatives of the quantile average. It is smaller or equal to 0. Or another equivalent definition is that if we consider all the quantile averages, and for every quantile average, if its breakdown point is smaller than the breakdown point, then the breakdown point of another quantile average, then this quantile average must be greater than another quantile average for a right square distribution. So this definition basically saying that for if a distribution there is an ordinals among the quantile averages, then this distribution is ordered. Yes, this is the definition, and this definition has very nice property. And for example, here is a necessary and sufficient condition that if we can convert it into the probability density function, the first quantile, if we plug in, and then it is always greater or equal to the probability density if we plug in the second quantile for a right square distribution. So, and this relation has a very nice property that if we consider a right square and a monotonic decreasing distribution, the first probability is since the first quantile is always greater, is always smaller or equal to the second quantile, and then since it is monotonic decreasing, so we can expect the probability density of the first quantile is always greater or equal to the second quantile, since and therefore it is always be gamma ordered. And for unimodal distribution, the case is similar, and because if the mode if the quantile first quantile is greater than the mode, if it is greater than the mode, and then for the second quantile, and then for the second quantile, because it should be always greater than the first quantile. So and this is this part according to the definition of unimodal distribution, this part is monotonic decreasing. So we just finding a monotonic decreasing part, and therefore it is always this relation is always valid. So this suggests that although a distribution might not be strictly gamma ordered, but this inequality holds for many quantile averages for most unimodal distributions following the mean gamma median mode inequality, because for such inequality it is normally a skew distribution. And furthermore, we can classify, because the many common right skew distributions are partial bounded. Partial bounded, therefore, it indicates a convex behavior of the quantile function when the epsilon is approaches 0. So we can further consider the second derivative of the quantile average, and if we assume it as greater to 0, and then plus the first order ordinators, and then analogously the Knuth gamma ordinators can be defining as this equation. And indeed, we check many cases, many unimodal cases of this in these four cases, the Weibull distribution and the gamma distribution. In most cases, the first three ordinators is valid, and the violation just occur when the schooners, when the distribution is nearly symmetry. So. And therefore we provided a new class of distribution based on the signs of derivatives of the quantile average, and we will later show that it plays a very fundamental role in robust statistics.